Hi, welcome everyone. Welcome to this course. So we are discussing about Markov processes, and we, discussed discrete Markov process and associated. We solve the associated probability distributions, and later we get the stationary state or steady state distribution for those process. Now we will, uh, you know, move our attention to the continuous Markov process, and in the last leg of this discussion, which is about Fokker Planck equations and Ornstein Uhlenbeck process. So let me start. So this is continuous Markov processes. Okay. So basically, let's say a continuous Markov process. Let's say, let us take a continuous Markov process x t. Okay, so basically the sample space of the random variable will be continuous set of values, right? The sample space of the random variable is some continuous set of variables. Okay, so basically if you write the counterpart for a stationary continuous process, so for a stationary continuous Markov process, you can write that Pn at the nth step or nth time xn tn, given that xn minus 1 tn minus 1 dot dot x1 t1 is equal to product of this probability, that n minus 1 number of probability product of p of x r plus 1 t r plus 1 minus tr xr, product of this times p of x1. So basically we are taking this thing that this will be so this is here the time translational invariance is assumed. So basically it will be, for r equal to 1, it will be t2 minus t1 x2 from x1. So transition probability from x1 to x2 given the time t1 to t2. Okay, so basically we are talking about this. Okay, so now, and this is for every n greater or equal to 2. So the stationary, so the fundamental quantity, so the fundamental quantity that characterizes a stationary continuous Markov process is the conditional density of p xt from x naught. So the stationary probability or stationary PDF p x is expected to be the is to be related to quantity. So the stationary probability density function, let's say p of x, that is expected to be like this: limit t tends to infinity, p of xt x naught, that becomes p of x. So it is actually independent of the initial value. So this is, so it is independent of the initial value x naught. So we have seen for the discrete Markov process, the conditional density satisfied the Chapman-Kolmogorov equation. So now, similar to discrete Markov process, this continuous case will satisfy the Chapman Kolmogorov equation. So that will eventually become like this. So p of xt given x naught is equal to dx prime p of xt minus t prime given x prime p of x prime t prime given x naught, where the t prime is in between t and 0. So this is equation 3. So and this integration should be the range of this integration should be from the allowed values of the random variable, and the transition from the using the transition probability, u- using that thing. So let again assume w of x prime dx be the probability per unit time of a transition from a given value x prime to the range of values x and x plus dx of the random variable. So therefore this wxx prime is the transition probability, right? Probability density, sorry. So wxx prime is the transition probability density. So then this chain equation then reduced to the master equation, namely d dt of p xt x naught is equal to dx prime p of x prime t x naught w of x prime minus p of xt given x naught w of x prime x. So this is equation number then 4. And what will be the initial conditions of the conditional probability? And the initial condition to the probability density will be p of x0 x of 0 x naught is delta function x minus x naught. Okay, so that we have to solve. Okay, so now we are coming to be a this thing. So Fokker Planck equation. So this equation 4 is a linear equation for the conditional probability density function, and it is an integral differential equation. So the equation 4 is a linear equation for the conditional PDF P x t x naught, and it is also integral differential equation. Integral differential equation. So solving it exactly is very difficult. Solving this equation exactly is very difficult. So that's why we'll use some tricks. Now one approach to this, it would be if we convert this part partial differential equation. Okay, but converting this part, one approach could be to convert the right hand side to partial differential equation, but that would take then infinite order of the partial derivatives. But there comes infinite order of partial derivative del x, and this is called the Kramer's Moyal expansion. This is called the Kramer-Moyal's expansion of the master equation. Okay. So in many physical conditions, the master equations can be either reduced or can be approximated to the second order partial differential equation. So in many physical cases, the master, but that would be since Kramer-Moyal expansion will be difficult, so we will not go into that. If we get some time, we can discuss it, but let's not go into that for now. that the master equation can be reduced or well approximated well approximated to a second order differential equation. Second order differential equations. Okay. So then it becomes del t p of xt at x naught becomes minus ddx of a1 x p xt x naught plus half of del 2 del x2 a2x p of xt x naught. So let me write this as equation number 5, and thus functions will be defined later. So these functions a1x and a2x will be defined later, and this equation equation 5 is called forward Kolmogorov equation, or more commonly in physics or physics literature, the Fokker Planck equation. The Fokker Planck equation. It is more commonly known as that. Now the diffusion equation we have studied earlier, that is a special case of Fokker Planck equations, and there in the Smolukowski equations we have considered the diffusion equation in the presence of a constant external force, and that equation is called Smolukowski equations. Now let me go into this, that now in mathematics all the continuous Markov processes whose conditional densities satisfy Fokker Planck equation are called diffusion process. So in mathematics all continuous Markov processes whose conditional density satisfy the Fokker Planck equation are called diffusion processes. Diffusion processes. So let's go into this thing. Okay. And these functions and the functions a1x and a2x are referred referred to as the drift coefficient, the drift coefficient and diffusion coefficient and diffusion coefficient respectively. Okay, so they are actually essentially the first two moments of transition rates. So they are basically first two moments of the transition rate. So the precise definitions, if you write the expression, then a1x becomes dx prime x prime transition rate x plus x prime given from x, and a2x is dx prime x prime whole squared of x plus x prime x. So basically they are giving these moments. So let me, this equation number 6, and the solution of Fokker Planck equation itself is a non-trivial, and the main technical part for that non-triviality is that the differential operator which is at the right hand side, like this differential operator in the right hand side of the equation, it's not a self-adjoint operator. So, and but we can deduce some feature of this, and we will look into that now. Now some features of the equations, however, can be deduced quite easily, starting from writing down these equation this in a form of continuity equations. Okay, so so basically we can deduce some features some features from equation 5 from equation 5 so equation 5 can be written can be written in the form of in the form of an equation of continuity, equation of continuity, like d dt of p xt x naught plus del x of j xt x naught is equal to 0. You see what I'm trying to do here, right? Because you have seen this kind of equations earlier in the diffusion equation when you have written the Smolkovskiy equation and all these things. So where the probability density, sorry, probability current density, probability current density J is given by, so J xt x naught is equal to minus del or x half a2x p of xt x naught plus a1x p of xt x naught. Basically, if you take del x and this side will be minus, so you can write like this. Okay, so this is equation 8. So what we were saying, that we can write this equation like this probability current density as it, you know, follows, as it follows these equations. Okay, so now basically it consider this case. Now consider the case where t actually tends to infinity. Then for like, so we can write then, because since it is going to the equilibrium, then we can write it does not depend, it shouldn't depend on t, then x naught should approach p of x, means the state at in which it is in. So then correspondingly jxt tends to stationary current, where j stationary x becomes minus ddx of half a2 of x p of x plus a1x px. Let's say this is equation 9. Obviously, from it follows d of p of x dt is equal to 0 because p of x does not depend on time, right? So then you can write this equation ddx because there is no time dependence in the equations. Now you can write, so now the equation 5, I think 5 becomes, equation 5 becomes d stationary dx is equal to 0, so that stationary current density JSTx is actually independent of x. So now if that is the case, then this term can also be, this is then constant, because since this is del del px, this is, then it will be constant, right? So then it follows, so JST becomes constant. So then it follows it follows following thing, that the stationary density stationary density itself can be written by solving first order ordinary differential equation. Okay, so that's that. Then now that means it becomes ddx of half a to x p of x minus a1x px is equal to constant. Okay, then it becomes 10. Okay, so that is the thing. So now we will move our attention to a special stationary Gaussian Markov process. Okay, so that process is the OU process, or called Ornstein Ornstein Uhlenbeck process. Ornstein Uhlenbeck process. So among all the continuous Markov process, there is a very unique one. So there is only one continuous random process that is stationary Markov as well as Gaussian and this is the Ornstein Uhlenbeck process. So what do you mean by Gaussian process is that by a Gaussian process, it means that all the joint probability densities of the random variable are Gaussians in functional form and the range of the variable, we should accept the range of the variable to be minus infinity to infinity. So now Ornstein Uhlenbeck process, we call it OU process. So now we can write this, the Ornstein Uhlenbeck process corresponds to the case when the drift coefficient is proportional to x and the diffusion coefficient is a constant. So that makes a1x is equal to minus a1x, and a2x is equal to a2, where a1 a2 is equal to positive constants. So if we take these two terms a1x and a2x, which is the drift term and diffusion term, like this, then our Fokker Planck equation becomes immediately the Fokker Planck equation readily becomes for this case as ddt of, so then it readily becomes the Fokker Planck equation readily becomes ddt of p xt x naught is equal to a1. So basically you put this here like this, so minus a1 x px, like this constant term will be there, so this will becomes minus a1x a1 del x of a1 del x of x p of xt x naught plus a2 by 2 del 2 del x2 p of xt x naught. Okay, so this is equation 11. So if you do the dimension analysis, then you can get the dimension of a1. Okay, so probability, so in this equation there is uh, here, let's say if we talk about this, then there is t, there is x, ax1 a1x, so a1 will be then t, just because there is delta x also. So the physical dimension of a1 is 1 by time, that is p minus 1, and dimension of a2 then will be a2 by x square will be 1 by t, so it will be x square by t, so a2 will be mod of x dimension of x square by dimension of time, which becomes L square t minus 1. So the initial condition is given here. So let's say initial condition, let's say that is p of x0 x naught is delta x minus x naught. Okay. And also the simplest boundary condition is that as x tends to infinity, at it blows up, so that probability will also become 0. And also natural boundary condition natural boundary condition is p of xt x naught is equal to 0 as x tends to plus minus infinity. So the solutions of this equation 11 actually satisfies these conditions, can be evaluated, but let's discuss the physical features of the solutions. Okay. So main physical features of the solution. Okay. So first thing first, the conditional density starts at t is equal to 0 as a delta function peak at x naught and widens and widens as t increases. So, and it is a Gaussian for all t greater than 0 and attains a limiting Gaussian form as t tends to infinity. That one is like evident, right? So now again, as t increases, as t increases, the mean value of x of t, and hence, since this is Gaussian, hence the peak the where the peak of the Gaussian is, the peak of the Gaussian or the bell curve drifts monotonically to 0 like uh, decaying exponential function of t. So basically it do just like this. Okay, so it monotonically drifts towards this. And second part is that we will all calculate these things one by one. Second is third is the variance of xt increases xt increases monotonically from 0 and tends to a saturation value tends to a saturation value as t approaches infinity. So, and the fourth part is the autocorrelation function of xt decays to 0 exponentially in time exponentially in time with a characteristic time constant given by 1 by E1. So that is the main feature of the Ornstein Uhlenbeck process. So we can solve these equations by this. Okay, so basically to solve it, so if you know the mean, so let's solve, let's do not solve it, rigorously. Let's solve it with some logic. Okay, so first is, let's define first moment, which is mean mu of xt as this x of t, which is, let's say, minus infinity to infinity dx x p of xt x naught and x square of t, by definition that is to be minus infinity to plus infinity dx x squared p of xt x naught. So let's say these are the equations. Okay. Equation number 12. Number 12. Then you can write that these moments also satisfy the first order differential equation in time let's say you multiply this Fokker Planck equation by x. So if you multiply this equation by x and then if you do the integration over x, then it becomes, so if one multiplies both sides of the equation by x and x square respectively, and then integrate over x. So after some simplification, some simplification it becomes two set of equations. We can get, let's say, ddt of moment of xt plus a1 moment of, like, first moment xt is equal to 0. Similarly, ddt of x square of t plus 2a1 of x square of t minus a2 is equal to 0. So let's say equation number 13 this is. Now it is important to see that this average is the conditional average, that is, they are averaged over all possible realization of the trajectories for the random processes, given that initial condition is x naught. So a point note the average is taken over all possible realizations of the random process xt given the specific initial value x naught. So therefore the initial conditions on the moments, so the initial conditions on the moments are basically x of 0 becomes x0 and x of 0, x square of 0, that becomes x naught square. Okay, so now you can write the solutions like this. So then xt, moment of xt, so solving equation 13, we get xt becomes mu x t as, so this will be x to the power e to the power minus a by t. So this is mod of x naught, mod of x naught into e to the power minus a1 t, which is x naught e to the power a1 t. Similarly, x square t becomes, so this is also a like integrating factor, you have to do the integrating factor, and that then it becomes a2 by a1 a2 by a1 so this is a2 by a1 plus x naught squared minus a2 by 2a1 e to the power minus 2a1 t. So these are equation 14 for all t greater equal to 0. So now basically you get this, and if you solve it for, now let's calculate the variance. The variance of xt, that becomes var of xt, that becomes sigma x square t is equal to x square t minus mu x square of t, which becomes, so this x square e to the power minus 2a1 t, that will cancels out, and that becomes a2 by a1 into 1 minus e to the power minus 2a1 t. That means, that's why our this point, that variance increases monotonically from 0 and tends to a saturation value as t. Okay, because t is equal to 0, this means this is 1, so 1 1 minus equals 0. So that proves our discussion point discussion point discussion point that variance is 0 at t is equal to 0, and then it monotonically increases to a limiting value, not a the, to the limiting value a2 by a1, and it is independent of the initial conditions too, independent of initial condition too. Okay, so now I will do this. I will do for these expressions that how this expression is coming. I will do this. So, and then I will stop. So, we have written that this term. Now we know del p xt x naught by dt is equal to a1 del x of xp xt a1 del x of x1 pxt x naught plus a2 del x2 a2 by 2 del x2 p of xt x naught. Now if you multiply both sides by x squared and integrate over x. So if you do that, then this becomes x square of, so in this term there is del t, so that will not change it. So this becomes then ddt of, so this is, there is only ddt of, so then this becomes, first term, this becomes ddt of x square pxt x naught dx. So that actually makes it to be ddt of average of x square t. Now this term and this term, this term and this term, so here this becomes a1 x del x x, so this is x squared del x p of xt x naught, and then integrating over this. So there so if you take the integration here, then it becomes, so for, let's say this is the integration, this is 2x square pxt x naught minus infinity to plus infinity, so this blows off 0 plus, sorry, minus a1 2x, after integration this becomes 2x square p xt x naught p xt x naught, this, so then this becomes, if you take integration, this is 2a1 mod of x square of t, right? Now this is in this region, so this is this, and this one a2 by 2 x square del 2 del x2 p of xt x naught, this, for the first thing, it becomes a2 by 2 2x del x p xt x naught minus a2 by 2 2x del x p of xt x naught, so this blows up because the gradient is 0, and this term becomes minus a2 by 2 2x p of, no, this is x square, this is 2x, similarly dx p of xt x naught, this is becomes 0 plus a2 by 2, further this is 2, and this becomes p of xt x naught, so there is some dx, and pxt dx integration, this will give you 1, right? So then this becomes a2 by 2 into 2 is equal to a2. Now substitute these things here, then your equation becomes d dt of x square of t is equal to a1, this is a1 x square of t plus a2, so this is minus 2a1 minus 2a1, so after rearranging you get 2a1 x square t1 So you proving these equations 14. So this is how to get second equation of equation 14. Second equation of equation 14. Okay, so we discussed everything. So we'll stop here, and next we will see. So our main theoretical part in this again is finished. So we will last talk about the active Brownian particle and randomable particle, and some computational implementations, and then we will finish it with some additional exercise problems. Okay, so I'm stopping here.